In this section, I'm going to introduce a number of properties of the Fourier transform and some common Fourier transform pairs. Also, I'll show how we can exploit properties of the Fourier transform in order to more easily solve problems, such as computing the Fourier transforms of functions. This slide and the next slide contain tables summarizing a number of key properties of the Fourier transform. Later in this section, I'll be introducing each of the properties listed on this slide in detail and giving examples of how these properties can be used. This slide continues the list of key properties of the Fourier transform from the previous slide, and again later in this section I'll be introducing each of the properties listed on this slide in detail and give examples of how these properties can be used. When solving problems using the Fourier transform, we'll often find ourselves needing to compute the forward or inverse Fourier transform of certain commonly occurring functions. To assist with such computations, we often rely on a table of Fourier transform pairs. An example of such a table is shown on this slide. In this table, we have a column labeled little x of t, and in this column we have the formulas for a number of different functions listed, and then we have a column labeled big X of omega. And what this column has is the corresponding Fourier transforms of the functions in the previous column. So for example, if we wanted to find the Fourier transform of a function that has the formula signum of t, we can simply look this up in the other column. It would be a function which has the formula 2 over j omega. Or if we wanted to find an inverse Fourier transform, suppose that we have a Fourier transform function which has the formula 2 pi delta of omega, we can look up the inverse Fourier transform of this function in the table by simply going over to the other column. It would be a constant function equal to 1 in this case. Later, when we're solving problems using the Fourier transform, we'll often find ourselves referring to a table such as this in order to simplify the process of computing forward and inverse Fourier transforms. The first property of the Fourier transform that I need to introduce is the linearity property. Arguably, this is one of the most important properties of the Fourier transform, and what this property says is the following. If we have a function little x1 with the Fourier transform big X1, and we have a function little x2 with the Fourier transform big X2, then we automatically know the Fourier transform of any linear combination of the functions little x1 and little x2. In other words, the Fourier transform of a summation of this particular form here, where a1 and a2 denote arbitrary complex constants. And in particular, the Fourier transform of this particular linear combination is the corresponding linear combination of the individual Fourier transforms big X1 and big X2. At this point, I'd like to consider an example to illustrate how we can make use of the linearity property, and in particular, I'd like to consider example 6.7. In this example, we're asked to use properties of the Fourier transform and this particular Fourier transform pair here in order to find the Fourier transform big X of the function little x, where little x is given by this particular formula here, and a and omega naught that appear in this expression are real constants. So in order to do this, what we're going to need to do is rewrite this cosine function as a pair of complex sinusoidal terms, because we want to try to use the given Fourier transform pair, this pair here, which means that we need to express the Fourier transform that we're trying to calculate in terms of terms that look like this complex sinusoidal term. So we can do this quite easily. We can take the cosine function here and use Euler relationships to rewrite the cosine function as a pair of complex sinusoidal terms, in other words, using this highlighted relationship here. So when we take the Fourier transform, what we're going to end up with when we substitute the cosine function with the pair of complex sinusoidal terms is we end up with this next line here. And at this point we can use the linearity property, because what we're doing is we're taking the Fourier transform of a linear combination, basically a linear combination of two complex sinusoidal terms. So we can interchange the order of the Fourier transform operation in the linear combination, which gives us this next line. So here we've used the linearity property. And then using the given Fourier transform pair, in other words using this Fourier transform pair here, we can take the Fourier transform of e to the j omega naught t, in other words this highlighted function here, and e to the minus j omega naught t. We can take the Fourier transform of this expression, again using this Fourier transform pair here, because both of these terms, in other words both of these Fourier transforms that we need to take, are of the same form. They're both of the form e to the j some constant times t. So using this Fourier transform pair, what we end up with is this next line. And then of course we can cancel the 2's that appear in these terms here and get to our final answer, which is this answer here. And this answer can be equivalently expressed using this double arrow notation below. This is not really necessary, it's just restating the solution to the problem in a slightly different form. The thing on the left side of the double arrow is our original function, and then the thing on the right side of the double arrow is its Fourier transform. The next property of the Fourier transform that I need to introduce is the translation or time domain shifting property. And what this property says is the following. If I have a function little x that has the Fourier transform big X, and then I apply a time shift to the function little x, where I shift the function little x by t0, where t0 is an arbitrary real constant, the effect that this has on the Fourier transform capital X is it multiplies the Fourier transform by a complex sinusoid, where this constant t0 that appears in the complex sinusoid is determined by the amount t0 that we're shifting the function little x by. At this point, I'd like to consider an example to illustrate how we can make use of the translation property, and in particular I'd like to consider example 6.9. In this example, we're asked to find the Fourier transform big X of the function little x, where little x is given by this particular formula here, and the a, omega naught, and theta are real constants. Now the first observation we can make is that if we didn't have this plus theta term, and we also didn't have this constant capital A, we would already know how to find the Fourier transform of this function because we have this pair here from our table of Fourier transform pairs, and in particular we know how to find the Fourier transform of cos omega naught t. So really in this problem what we need to figure out is how to deal with this plus theta and how to deal with this constant capital A. Now rather than trying to combine all of these ideas together at once and try to solve the problem all in one step, which would be very error prone, what I'm going to do here is use a much more systematic approach. So what I'm going to do is I'm going to take this equation here, which effectively we're being asked to find the Fourier transform of in this problem. In other words, really what we're being asked in this problem is to take the Fourier transform of both sides of this equation. Now what I'm going to do is I'm going to split this equation into two smaller equations in order to make the process less error prone. And what I'm going to do in particular is I'm going to define a function which is equal to a cos omega naught t, and I'm going to define this as being v of t. So in other words, this particular function here is the function x without the plus theta term. And because of this, the relationship between the function little x and the function little v is given by this equation that I've labeled equation 2 here. In other words, the function x is just the function v shifted by minus theta over omega naught. Essentially a time shift has been applied to the function v to get to the function x. So essentially what we've done is we've taken our original equation, this one here, and we've decomposed it into two simpler equations, which I've labeled as equation 1, this equation involves little v, and equation 2, which involves little x and little v. What we're going to do next is we're simply going to take the Fourier transform of each of these equations, equation 1 and equation 2. So I'll start with equation 1. So if we take the Fourier transform of both sides of this equation, on the left-hand side, when we take the Fourier transform, by definition we just get big V. So this gives us big V of omega on this line here. When we take the Fourier transform of the right-hand side, we're going to simply end up with this right-hand side that's here. And we can make a few observations. First is that because of the linearity property of the Fourier transform, we can pull this constant A out of the Fourier transform operation. So really what we're left with is just taking the Fourier transform of what remains, which is the cos omega naught t. And for this we can simply look up the answer in our table of Fourier transform pairs, in other words by looking up this particular pair here, and the Fourier transform of cos omega naught t is given by this expression here. So we can simply substitute this highlighted expression for the Fourier transform of cos omega naught t, and then multiplying as well by a, that gives us this next line here. So we have the Fourier transform capital V at this point. Now we're going to take the Fourier transform of the second equation, the one that I've labeled by 2 here, equation number 2. If we take the Fourier transform of both sides of this equation, on the left-hand side, when we take the Fourier transform of little x, we simply get big X by definition, so that's this left-hand side here. when we take the Fourier transform of the right-hand side, because of this shift that we have, and remember you have to read time shifts with a minus sign here, so what we have is v of t minus, and then minus theta over omega naught. In other words, the amount we're shifting by is minus theta over omega naught. So bearing that in mind, when we take the Fourier transform of the right-hand side, we can apply the time shifting property, which says that when you shift by a certain amount, you're going to multiply the Fourier transform by e to the minus j omega, and then the amount that you're shifting by. And in this case, we're shifting the function by minus theta over omega naught. So if we multiply this minus sign, or this minus 1 with this minus 1 here, they cancel, and what we're left with is this particular factor here. And this is going to multiply the Fourier transform of v. Now we don't want to leave our answer for the Fourier transform of x in terms of this expression here, because it has this quantity v which was not in the original problem statement. V was introduced when we introduced this equation here, which was not part of the original problem. So what we'd like to do is we'd like to get rid of this capital V. And if we make an observation that above we already have an equation for v, we have that capital V is equal to this right-hand side here, we can simply substitute this highlighted expression for v of omega, which gives us this next line. And this is essentially our final answer. Now we have our answer expressed in terms of quantities that are only belonging to the original problem statement. We don't have things expressed, for example, in terms of the function v or capital V. And of course we could rewrite this using double arrow notation as well, but this is not really necessary. This is basically just restating what's stated on the previous line. The next property of the Fourier transform that I need to introduce is known as the modulation or frequency domain shifting property. And what this property says is the following. If I have a function little x that has the Fourier transform big X, and then I take that function little x and I multiply it by a complex sinusoid, in other words a function of the form e to the j omega naught t, where omega naught is an arbitrary real constant, the effect that this has on the Fourier transform of the function big X is it applies a shift to the function, a shift by omega naught. Now I'd like to consider an example to illustrate how we can use the modulation property. And in particular, I'd like to consider example 6.10. In this example, we're asked to find the Fourier transform big X of the function little x, where little x is given by this formula here, and omega naught is a real constant. Now the first observation we can make is we already know how to deal with this cos omega naught t factor, because this appears as one of the pairs in our Fourier transform table. In other words, this particular pair here that I've highlighted. So if we didn't have this cos 20 pi t here, we would know how to find the Fourier transform just by looking it up in our Fourier transform table. But so somehow we need to deal with this cos 20 pi t. And what we're going to do here is we're going to use the modulation property in order to deal with this cos 20 pi t. And in particular, what we're going to do is we're going to rewrite the cos 20 pi t as a pair of complex sinusoidal terms. In other words, we're going to use a relationship like this highlighted relationship here to rewrite this cos 20 pi t as a pair of complex sinusoids. So if we do this, when we take the Fourier transform of this equation, what we're going to end up with is this next line here. And what we've done is we've taken the cos 20 pi t and we've rewritten it as a pair of complex sinusoidal terms. Now at this point we can then distribute this cos omega naught t factor over the other two terms, which gives us this next line. And then we can use the linearity property, because essentially what we have on this line, the thing that we're taking the Fourier transform of, it's a linear combination. So we essentially have a Fourier transform of a linear combination. But we can interchange the linear combination and the Fourier transform and write them in the opposite order. So we have a linear combination of Fourier transforms. This is what appears on the next line. So we're just using the linearity property. So now what we need to deal with are two Fourier transforms, in particular this first Fourier transform here, where we have a complex sinusoid times cos omega naught t, and then we have this Fourier transform over here where we have a complex sinusoid times again cos omega naught t. So if we focus on the first of these two Fourier transforms, if we didn't have this complex sinusoidal factor, if we just had the cos omega naught t, this would be very easy to take the Fourier transform of. Basically it would just be the result that we have here. But because we have this complex sinusoid, we have to worry about what effect this has on the Fourier transform. And we know from the modulation property that multiplying by a complex sinusoid will introduce a shift into the Fourier transform. So what we're going to end up with, instead of just getting the Fourier transform of cos omega t evaluated at omega, because of the shift that's introduced by multiplying by this complex sinusoid, in particular it's going to introduce a shift of 20 pi. Because of this, we're going to evaluate the Fourier transform of cos omega naught t at the point omega minus 20 pi, instead of evaluating it simply at omega. And it's a similar sort of story for the second Fourier transform that we have here. If we just ignore this complex sinusoidal factor to begin with and focus on the cos omega naught t, if we take the Fourier transform, we would just get this result here from our Fourier transform table. But this is not going to be the correct answer because we have this complex sinusoid that we're multiplying by. So we have to compensate for the fact that we're multiplying by this complex sinusoidal factor. And if you recall, the modulation property says that when we multiply by a complex sinusoidal factor, the effect that this has is it introduces a shift in the Fourier transform. And in this particular case, the constant that we have appearing in this exponential, other than the j, is minus 20 pi. So this is going to introduce a shift of minus 20 pi. So in other words, what we're going to have is not the Fourier transform of cos omega naught t evaluated at omega, but rather it's going to be evaluated at omega minus 20 pi. In other words, omega plus 20 pi, which is this expression that's highlighted here. Now we need to take the two Fourier transforms on this line. So if we focus on the first Fourier transform, this one here, we need to take the Fourier transform of cos omega naught t. So from our table of Fourier transform pairs, we know that this is equal to this expression here. So we can copy this highlighted expression onto the next line. However, all the places where we would normally write omega in this expression, we have to change them to omega minus 20 pi because we're evaluating the Fourier transform result here not at omega, but at omega minus 20 pi. So this is the reason for this substitution here being performed. And it's a similar story for the second Fourier transform. When we take this Fourier transform here, again we're taking the Fourier transform of cos omega naught t. So from our table of Fourier transform pairs, we have this particular result for the Fourier transform, which is just copied down below here. Except all the places where we would normally write omega, we have to replace the omegas by omega plus 20 pi, because we're not evaluating the Fourier transform result at omega here, we're evaluating it at omega plus 20 pi. So that's the reason for this substitution. And then at this point we can just evaluate these terms here and expand out and rearrange the terms to get to our final answer. The next property of the Fourier transform that I need to introduce is the dilation property, also known as the time or frequency domain scaling property. And what this particular property says is the following. If we have a function little x whose Fourier transform is big X, and we take the function little x and apply a time scaling transformation to it where we're time scaling by a factor of a, where a is an arbitrary non-zero real constant, the effect that this has on the Fourier transform is twofold. The first effect that we get is due to this division by a in the expression that we have here, which causes a frequency domain scaling. And the other effect that we have is due to this scale factor of 1 over absolute value of a, which causes an amplitude scaling of the Fourier transform. Now I'd like to consider an example to illustrate how we can use this particular property of the Fourier transform. And in particular, I'd like to consider example 6.11. In this example, we're asked to find the Fourier transform big X of the function little x, where little x is given by this formula here, and a is a non-zero real constant. In other words, little x is just a time-scaled version of the rectangular function, specifically a version of the rectangular function that's been time-scaled by a factor of a. And in particular, to do this example, we're asked to use this particular Fourier transform pair here. And you'll notice if you compare this particular Fourier transform pair, which involves rect of t, to the function x that we're given, these two functions are related by a time-scaling operation. Here we have rect of at, here we have rect of t. So in order to do this problem, we're going to need two pieces of information, or use two pieces of knowledge. We have to use the fact that we have this particular Fourier transform pair, and we're also going to have to use the the time scaling property of the Fourier transform. Now, instead of trying to combine these two steps together and do them all at once, which can be quite error prone, I'm going to do this in a more systematic way. I'm going to take the equation that we're given for x here, and I'm going to split it into two simpler equations. So I'm going to start out by creating a function that I'm going to call little v, which is defined to be equal to rect of t. So essentially the function little v that's defined in equation 2 here is simply the rect function that appears here, in other words the function x, but without this constant a. And then given that v is defined in this way, the relationship between the function little x and little v is given by equation 3, in other words this equation that I've highlighted here. In other words, the function x is simply the function v time scaled by a factor of a. And what we're going to do next is we're going to simply take the Fourier transform of these two equations, equation 2 and equation 3. So I'll start out with equation 2. We'll take the Fourier transform of this equation. So if we take the Fourier transform of the left-hand side, little v, we simply get the Fourier transform big V by definition. So that's this left-hand side here. And when we take the Fourier transform of the right-hand side of equation 2, in other words rect of t, by virtue of this Fourier transform pair here, we simply get sinc of omega over 2. So this is where this right-hand side here comes from. So we have the Fourier transform big V. Now we're going to take the Fourier transform of equation 3. So when we take the Fourier transform of the left-hand side, the Fourier transform of little x is just big X by definition, so that gives us this left-hand side here. And then we're going to take the Fourier transform of the right-hand side, V of at. And in this case, we need to use the time scaling property of the Fourier transform. So if you recall, when we apply the time scaling property, this has two effects on the Fourier transform V. The first effect is we're going to get a frequency scaling effect, a frequency domain scaling effect, I should say, by a factor of 1 over a. And the other effect that we get is an amplitude scaling by a factor of 1 over absolute value of a. Now we don't want to state our final answer in this form. I mean, technically what we have here is an expression for the Fourier transform big X, which is what we're being asked to find in this problem. But this is expressed in terms of this function capital V. But capital V was essentially something that we introduced into the problem ourselves in order to make it less likely that we make a mistake in solving the problem. And this was effectively introduced by way of equation 2. So we don't really want to state our final answer in terms of capital V. We'd like to get rid of this capital V. And the way we can do this is we can observe that on the previous line we have an equation for the function capital V. So what we can do is we can substitute in this expression sinc omega over 2 for V of omega. So if we do this substitution in this line here, what we get is the next line, which is our final answer. So we have the Fourier transform of little x, which is denoted by big X here, is given by this right-hand side expression. And of course we can write this as well with double arrow notation, just as an alternative way to represent our final answer. The next property of the Fourier transform that I need to introduce is the conjugation property. And what this property says is the following. If I have a function little x with the Fourier transform big X, and I then take the complex conjugate of the function little x, the effect that this has on the Fourier transform is twofold. First of all, the Fourier transform has a time reversal transformation applied to it, which is associated with this minus sign here. In other words, omega has been replaced by minus omega. And the other effect that we have is that the overall Fourier transform expression has been conjugated, which is due to this complex conjugate operation here. Now I'd like to consider an example to illustrate how we can make use of the conjugation property. And in particular, I'd like to consider example 6.12. In this example, we're asked to prove a particular property of the Fourier transform. In particular, we're asked to show that if the function little x is real valued, then its Fourier transform big X is conjugate symmetric. In other words, big X satisfies a relationship of this form here that's highlighted. Now to do this, what we're going to use is the conjugation property. So as our starting point, we've just stated the conjugation property in terms of an equation. And what we're going to do is we're now going to observe that since the function little x is a real valued function, conjugating the function doesn't change anything. So we can drop this conjugation operation from the left-hand side, since it's not going to change anything by doing so. And this gives us on the left-hand side the Fourier transform of little x. But the Fourier transform of little x by definition is just big X. So we have this final equation here, but this equation is simply saying that the function big X is conjugate symmetric, which is what we were asked to show. The next property of the Fourier transform that I need to introduce is the duality property. But before I introduce a formal statement of the duality property in terms of mathematical notation, I'd first like to explain in less formal terms what the duality property is saying. So recall that with the Fourier transform we have two key equations. We have the Fourier transform analysis equation, which is this equation here, and we have the Fourier transform synthesis equation, which is this equation here. Now I've written these two equations using some different variable names from the ones that we typically use in order to highlight the similarities between these two equations. And in fact there's only two differences between these two equations. The first is that in the exponential function that appears in these equations, there's a sign difference in the parameter for this exponential. In this case, the exponential has a negative sign in it, whereas in the exponential function that appears in the other equation, there's no negative sign. So there's a sign difference in the exponential function between these two equations. The only other difference between these two equations is that the second equation has a factor of 1 over 2 pi, whereas the first equation has a factor of 1 that we don't bother to write. So in other words, the only difference between these two equations is they differ by a factor of 2 pi, and there's a sign difference in the parameter for the exponential function. And the significance of this is the following. Consider what happens if we use the wrong equation, in other words, the opposite equation from the one we had intended. So for example, suppose that our intention was to take the forward Fourier transform by using this equation, but instead by accident we used this other equation and we took the inverse Fourier transform. If we use the wrong equation, in other words the opposite one from the one we had intended, we almost obtain the correct answer. In other words, the answer that we would have obtained had we used the correct equation. More specifically, the wrong answer that we obtain will be wrong in a very particular way. Namely, it will be out by a factor of 2 pi and will also have a sign difference in the independent variable. So as long as we correct for these two differences, we can obtain the correct answer by using the wrong equation. And this is essentially what the duality property states. So with this said, we can now look at the formal statement of the duality property given at the top of this slide. So what the duality property says is the following. If a function little x has the Fourier transform big X, then if we take the Fourier transform of big X, we get this particular Fourier transform given on the right-hand side of the double arrow. But if we think about what we're doing here, notice that the thing that appears on the left side of the double arrow is big X, not little x. So in some sense we're probably using the wrong equation, because if we have a function that's already a Fourier transform, in other words the function big X, probably what we want to do is take the inverse Fourier transform of the function, not take the forward Fourier transform. But in this particular equation here, we're taking the forward Fourier transform of big X. So in some sense we're using the wrong equation from what we would want to use. But the duality property says this is okay, we can fix this. Now if the two equations that we have here, this equation and this equation, were actually identical, if they were the same equation, then the answer that we would get for the Fourier transform of big X of t would just be little x of omega. But because these two equations are not identical, we have to correct for the fact that we used the wrong equation. Because the two equations are not identical, it matters that we didn't use the right equation. They're not quite the same. But the duality property says we can correct for this. What we can do is we can take the answer, the wrong answer that we would get, which would be little x of omega, and we can correct it by flipping the sign of the independent variable, so all the omegas get replaced by minus omegas, and also multiplying the answer by a factor of 2 pi. So by making these adjustments, effectively we can use the wrong equation but still get to the right answer by fudging or adjusting the wrong answer that we get to make it correct. The duality property has many far-reaching consequences. For example, a number of properties of the Fourier transform can be grouped into pairs, where one property in the pair implies the other property due to duality. The duality property also has important implications with respect to the computation of Fourier transforms. Suppose, for example, that we're given a Fourier transform pair like the one that I've highlighted here, where we are effectively told that the function little x has the Fourier transform big X. So although this Fourier transform pair directly gives us one Fourier transform, in other words it tells us what the Fourier transform of the function little x is, this Fourier transform pair also gives us a second Fourier transform indirectly through the duality property. In particular, this Fourier transform pair allows us to infer what the Fourier transform of big X is. So not only does this Fourier transform pair give us the Fourier transform of little x in a direct manner, it also indirectly gives us the Fourier transform of big X. So effectively, using the duality property, we can double the number of Fourier transform pairs that we know. And this is very useful in practice, because often knowing more Fourier transform pairs is very useful for solving problems. At this point, I'd like to consider an example to illustrate how we can make use of the duality property. And in particular, I'd like to consider example 6.13. In this example, we're asked to find the Fourier transform big X of the function little x, where little x is given by this particular formula here. In other words, little x is a sinc function that's been time-scaled by a factor of 1/2. And in order to do this example, we're being asked to use this particular Fourier transform pair that we're given. And looking at this Fourier transform pair, you can see that it's not directly useful for solving this problem, because this particular pair gives us the Fourier transform of the rectangular function, but clearly the function that we're asked to find the Fourier transform of has nothing to do with the rectangular function. However, the function that we are asked to find the Fourier transform of, this function here that I've highlighted, is precisely the function that appears on the right side of the double arrow in our Fourier transform pair. So we can use the duality property in order to find the Fourier transform. So to begin with, what I'm going to do is I'm going to rewrite the Fourier transform pair that we're given, in other words this pair here, explicitly labeling the functions on each of the left and right side of the double arrow. So the function on the left side of the double arrow I'm going to call little v, so we have little v of t is equal to rect t. And then the Fourier transform of little v I'm going to denote by big V, so we have big V of omega is equal to sinc of omega over 2. And because this function big V is identical to the function little x, these are the same function because they have exactly the same equation that defines them, if we find the Fourier transform of big V, we also find the Fourier transform of little x because they're the same function. And we can find the Fourier transform of big V by using the duality property. In particular, we have from the duality property of the Fourier transform that the Fourier transform of big V evaluated at omega is equal to 2 pi little v evaluated at minus omega. In other words, we have this particular formula here from the duality property. And then we can substitute for little v, because the function little v is given by this equation here. So if we substitute in for little v, we end up with this next expression, this one here. And then we can observe that the rect function is an even function, therefore we can drop this minus sign and this won't change anything, which gives us this next expression. And this is essentially our final answer, because what we have here is the Fourier transform of big V, but because big V is equal to little x, this also corresponds to the Fourier transform, in other words this expression here, also corresponds to the Fourier transform of little x. In other words, we have this particular result here. The next property of the Fourier transform that I need to introduce is the convolution or time domain convolution property. And what this property says is the following. If I have a function little x1 with the Fourier transform big X1, and I have another function little x2 with the Fourier transform big X2, then the Fourier transform of the convolution of the functions little x1 and little x2 is given by the product of the Fourier transforms big X1 and big X2. In other words, the Fourier transform converts a convolution in the time domain into a multiplication in the frequency domain. And this suggests a particularly important application of the Fourier transform, which is that it can be used to avoid having to deal with convolution operations. Because if we have an equation that has convolutions in it, what we can do is we can take the Fourier transform of that equation, and when we do so, the convolutions will be replaced by multiplication operations in the Fourier domain. And this idea is very useful, for example, when working with linear time-invariant systems. At this point, I'd like to consider an example to illustrate the use of the convolution property, and in particular, I'd like to consider example 6.14. In this example, we're asked to find the Fourier transform big X of the function little x, where little x is the convolution of the functions little x1 and little x2. And in particular, little x1 and little x2 are given by these equations here. And we're told in this particular problem that we can make use of a Fourier transform table. So to approach this problem, what we're going to do to begin with is we're going to take the Fourier transform of this equation. So when we do this, this gives us this line here. And we need to then simplify the Fourier transform of the convolution of x1 and x2. And to do this, we use the convolution property. The convolution property says that this Fourier transform is simply going to be the product of the Fourier transforms of little x1 and little x2. In other words, it's going to be big X1 times big X2. So at this point, all we need to do is find the functions big X1 and big X2. So to do this, first of all, let's find big X1. So we're going to do this by taking the Fourier transform of this equation. So when we take the Fourier transform of this highlighted equation, we're going to get this particular equation here. And then we simply need to simplify this Fourier transform that appears on the right-hand side. So we have the Fourier transform of a real exponential times a unit step. And it turns out that this particular function appears in our Fourier transform table. So we can just read the answer out of our table, which turns out to be 1 over 2 plus j omega. Next, we find the function big X2. So we can do this by taking the Fourier transform of this equation that I have highlighted. So when we do this, we're going to get this equation here. And we simply need to simplify the right-hand side, which has the Fourier transform of the unit step function. And again, we can make the observation that the unit step function appears in our Fourier transform table, so we can simply read the answer out of our Fourier transform table, which turns out to be this particular formula here. So now we have the functions big X1 and big X2, so we can substitute them into the right-hand side here and simplify to get to our final answer. So this is what we do next. So if we substitute those functions big X1 and big X2 into the formula we're just looking at, we end up with this line here that's highlighted. And we can do some basic algebraic manipulation to get to this second last line here. And at this point, we can use the equivalence property to simplify the first term. Here what we can do is observe that by using the equivalence property, we can replace the expression that's highlighted in green with its value evaluated at omega equal to 0, which corresponds to where this delta function is non-zero. So if we do this, this green highlighted expression simplifies to pi over 2. And this gives us our final answer for the function big X of omega, which is this particular expression here. The next property of the Fourier transform that I need to introduce is the multiplication property, also known as the time domain multiplication property or frequency domain convolution property. And what this property says is the following. If I have a function little x1 that has the Fourier transform big X1, and I have another function little x2 that has the Fourier transform big X2, then the Fourier transform of the product of these two functions, little x1 and little x2, is given by 1 over 2 pi times the convolution of their corresponding Fourier transforms, big X1 and big X2. In other words, multiplication in the time domain becomes convolution in the frequency domain to within a scale factor of 2 pi. And by the way, don't forget about the scale factor, this 1 over 2 pi scale factor. It's a common mistake to leave it out. Now this particular property of the Fourier transform is the bad news with respect to the Fourier transform. What I mean by this is most operations that we need to deal with in problems that we solve as engineers are made much easier by using the Fourier transform. And we saw earlier that the convolution operation is much easier to deal with when we use the Fourier transform, because the Fourier transform effectively turns convolutions into multiplication operations. As we'll see later, the Fourier transform also makes it much easier to deal with derivatives and integrals. So if we're dealing with differential equations or integral differential equations, these equations are much easier to deal with as well using the Fourier transform. So really the one piece of bad news about the Fourier transform is that multiplication is not something that's necessarily so easy to deal with when we're using the Fourier transform. Now in practice, this is often not a big problem, because many types of problems that we can solve don't require the use of this particular property, at least if we're careful and don't use it unnecessarily. So in this sense, this particular property, although it's bad news, it's not too terribly bad in the sense that often we don't have to use this property. because there are other ways to approach problems that don't require the use of this property. At this point, I'd like to consider an example to illustrate how we can use the multiplication property, and in particular, I'd like to consider example 6.15. In this example, we're given two functions, little x and little y, that are related by this particular equation here, where omega c is a non-zero real constant, and we're asked to find an expression for the Fourier transform of y, which is denoted by big Y, in terms of the Fourier transform for x, which is denoted by big X. Before proceeding further, I just want to emphasize that the entire point of this example is to illustrate how we can make use of the multiplication property of the Fourier transform. For this reason, I'm effectively being forced to use this particular property in order to solve this problem. The reason why this is important to understand is that if we were presented with exactly the same problem, but not constrained to use the multiplication property of the Fourier transform in our solution, then we would most definitely not want to use the multiplication property to solve this problem. A much better way to solve this problem would be to rewrite the cosine function as a pair of complex sinusoidal terms and then use the modulation property of the Fourier transform. The use of the modulation property will lead to a solution in only a few simple steps and completely eliminate any need for convolution. With the preceding comments out of the way, let's proceed to solve the problem at hand. So the first thing that I'm going to do is I'm going to define a new function little v, which is given by this particular equation here. In other words, I'm going to redefine this particular quantity in the original equation to be v of t. And in anticipation of things to come, I'm going to take the Fourier transform of little v, because it turns out that I'll need this later. So we can do this with the Fourier transform table, because a Fourier transform for a function of the form of little v appears in our table. So just reading it out of the table, we end up with this particular Fourier transform for little v, which is denoted as big V. And then the next thing I can do is I can take the original equation that we are given, this equation here, and I can rewrite it in terms of the function little v that I've defined below. In particular, I can replace the cos omega ct here with v of t, and this gives me this particular equation here. Now I can proceed to take the Fourier transform of this equation. When I do this, this will give me the next line, this line here, and then I need to simplify this Fourier transform. We have the Fourier transform of the product of little x and little v. And to do this, I can use the multiplication property of the Fourier transform. And the multiplication property tells me that the result is going to be 1 over 2 pi times big X convolved with big V. And we can expand out this star notation in terms of a convolution integral, which is what's done on the next line here. And then we can next substitute in for the function capital V. Up above here we said that capital V was given by this particular formula, so we can substitute this in for big V here, and this gives us this next line. And then we simply need to simplify this convolution integral. So the first thing we can do is we can cancel some pi's, which gets us to this next line. And then we can split this integral into two separate integrals, which is what we've done to get to this next line. And what we're going to do next is use the fact that the delta function is even, so I'm going to replace this underlying quantity here with its negative, which is what I've done on the next line. So this highlighted quantity is just the negative of the underlying quantity on the previous line. And I'm going to do a similar thing with this underlying quantity here that I've highlighted. I'm going to replace it by its negative to get to this next line. And I can replace these quantities by their negatives because the delta function is even, so this won't change anything. And then what I can do next is I can regroup the terms that appear in this expression here and this expression here to get to the next line. In other words, to get to this particular line here. And then lastly, I can use the sifting property. Both of the integrals that appear on this line are of the form of the sifting property. And in the case of the first integral, in other words this integral here, this integral is going to simplify to the function big X evaluated for the value of lambda, which corresponds to the place where this shifted delta function is non-zero. In other words, it's going to be evaluated at lambda is equal to omega minus omega c. So when we evaluate big X of lambda at lambda equal to omega minus omega c, this gives me this term on the next line. And then in this integral over here, we're going to apply the sifting property as well. So this integral is of the form of the sifting property. And this whole integral is going to evaluate to x of lambda, evaluated at lambda equal to omega plus omega c. So here we're going to get on the next line big X of omega plus omega c. And then obviously we can multiply the 1/2 here into both terms to get to the last line, which is this line here, which is our final answer for the expression for big Y in terms of big X. The next property of the Fourier transform that I need to introduce is the differentiation or time domain differentiation property. And what this property says is the following. If we have a function little x with the Fourier transform big X, then the effect that taking the derivative of little x has on the Fourier transform is that it multiplies the Fourier transform by j omega. In other words, differentiation in the time domain becomes multiplication by j omega in the frequency domain. And of course, this particular property can be used repeatedly. So for example, if we have an nth order derivative rather than just a first order derivative, we can compute the Fourier transform by multiplying the Fourier transform not just by j omega, but by j omega raised to the nth power. And this particular property of the Fourier transform is really quite important in a practical sense, because this particular property suggests that the Fourier transform might be a very useful tool when working with differential or integral differential equations, in other words, equations that involve derivatives. And the reason for this is because this particular property of the Fourier transform implies that we can use the Fourier transform to change differentiation operations into multiplication operations, specifically multiplication operations that multiply by j omega. And arguably multiplication is a much simpler operation than differentiation. At this point, I'd like to consider an example to illustrate how we can make use of the differentiation property. And in particular, I'd like to consider example 6.16. In this example, we're asked to find the Fourier transform big X of the function little x, where little x is given by this particular formula here. In other words, little x is simply the first derivative of the delta function. So in our solution to the problem, we're going to begin by taking the Fourier transform of the equation that we're given here. So this is going to give us this next line, and this line is just repeated on the line below. And now what we need to do is we need to simplify this Fourier transform here. So we have the Fourier transform of the first derivative of the delta function. So the way we're going to approach this is by using the differentiation property of the Fourier transform, which simply says we ignore to begin with the derivative operation and just take the Fourier transform of delta. So that gives us the Fourier transform of delta here. And then to compensate for the fact that there's a derivative taking place, in other words this derivative here, we compensate by multiplying our Fourier transform by j omega. And next what we need to do is simplify this Fourier transform, the Fourier transform of delta. And this is something that appears in our Fourier transform table. The Fourier transform of delta is simply a constant function equal to 1. So we can replace the Fourier transform of delta evaluated at omega by the value 1. So now we have the Fourier transform of x evaluated at omega is j omega times 1, which obviously is just equal to j omega. So we have that the Fourier transform of little x, which is denoted by big X, is given by this particular right-hand side here. The next property of the Fourier transform that I need to introduce is the frequency domain differentiation property. And what this property says is the following. If we have a function little x with the Fourier transform big X, then multiplying little x by the independent variable t has two effects on the Fourier transform. The first effect is that the Fourier transform is differentiated, in other words a derivative operation is applied to the Fourier transform. And secondly, the Fourier transform is multiplied by the constant j. Now I'd like to consider an example to illustrate how we can use the frequency domain differentiation property. And in particular, I'd like to consider example 6.17. In this example, we're asked to find the Fourier transform big X of the function little x, where little x is given by this particular function here, and omega naught is a non-zero real constant. So what we're going to do to begin with is take the Fourier transform of this equation, which gives us the line below, which is repeated on the next line here. And what we need to do then is focus on simplifying this Fourier transform. So we have the Fourier transform of t cos of omega naught t. And essentially we can do this by using the frequency domain differentiation property. And what this property says is initially we can ignore the t and simply focus on the remainder of what appears in this Fourier transform operand, which is the cos of omega naught t. So we take the Fourier transform of cos of omega naught t, but then to compensate for the fact that there's this t here, what we have to do is two things. We first of all have to take the derivative of the result that we get, so this d here denotes a differentiation operation, and we also have to multiply by j. So what we're going to do next is we're actually going to find the Fourier transform of cos of omega naught t, and we can do this by looking this up in our Fourier transform table. In particular, we have this Fourier transform pair that's shown at the bottom here. So the Fourier transform of cos of omega naught t is simply given by this expression here. So we can substitute that expression in for our Fourier transform, which gives us this particular expression appearing on the next line. And we also have to carry along the derivative operation and the multiplication by j. So this is why we have this j here on this line and this d by d omega. We can then pull the pi out of the derivative operation to yield the next line. And then finally we can interchange the order of the derivative and the sum using the linearity of the derivative operator to obtain our final answer, which is on the next line. In other words, this particular expression here. So we found big X of omega is equal to this right-hand side expression. The next property of the Fourier transform that I need to introduce is the integration or time domain integration property. And what this property says is the following. If we have a function little x with the Fourier transform big X, then the effect that integrating little x has on the Fourier transform is that first of all the Fourier transform gets divided by j omega, and in addition we get this extra additive term here which involves the Fourier transform evaluated at 0. As we saw earlier, taking a derivative in the time domain is equivalent to multiplying by j omega in the frequency domain. Therefore, since differentiation is the inverse of integration, it makes sense that integration in the time domain should somehow involve division by j omega in the frequency domain. Since the Fourier transform effectively converts integration to an operation involving division, particularly division by j omega, this suggests that the Fourier transform could be an effective tool for dealing with integration. In particular, if we have an equation involving integrals of the form handled by the integration property of the Fourier transform, these integrals can be converted to division operations by taking the Fourier transform of the equation. For this reason, the Fourier transform can be a very useful tool when working with integral or integral differential equations, in other words, equations involving integrals. At this point, I'd like to consider an example to illustrate how we can make use of the integration property of the Fourier transform, and in particular, I'd like to consider example 6.18. In this example, we're asked to find the Fourier transform big X of the function little x, where little x is the unit step function. And in particular, we're asked to solve this problem using the integration property of the Fourier transform. So the first thing that we're going to need to do is represent the unit step function in terms of an integral which is of the same form as the integral that appears in the integration property of the Fourier transform. So the first observation we can make is that we can represent the unit step function, or equivalently the function little x, using an integral of the form shown on this line. So at this point we can now take the Fourier transform of this equation, which gives us this next line here, and now we need to simplify this Fourier transform. So to do this, we're going to use the integration property of the Fourier transform. And the first thing that we're going to do is we're going to simply ignore the integration part and focus on the integrand, and take the Fourier transform of the integrand, which is just going to give us the Fourier transform of the delta function, evaluated at omega. But to compensate for the fact that there's this integration happening, we have to take this result that we get, this Fourier transform of delta evaluated at omega, and divide by j omega. So this is this particular factor here. And also to compensate for the fact that there's this integration happening, we also have to add in this extra term, which involves the Fourier transform of the integrand evaluated at 0. So we have the Fourier transform of the delta function evaluated at 0. And we can very easily determine the Fourier transform of the delta function. This is one of the functions that appears in our Fourier transform table. The Fourier transform of the delta function is just a constant function equal to 1. So this particular expression here, f delta of omega, is a constant equal to 1. So we can replace that by 1 on the next line. And similarly, this expression here, f delta of 0, is also a constant equal to 1. So we can replace this by 1 on the next line. And of course, multiplying by 1 doesn't change anything, so we can drop out the 2 multiplications by 1 on this line to get to our final answer, which is this expression here. So now we have that the Fourier transform of the unit step function, which is denoted by big X here, is given by this right-hand side expression. The next property of the Fourier transform that I need to introduce is Parseval's relation. Since this property relates to the energy of a function, I want to start by recalling that the energy of a function x is given by this particular quantity here. In other words, we take the magnitude of the function x, we square it, and then integrate over the domain of the function. With that in mind, Parseval's relation says the following. If we have a function little x with the Fourier transform big X, then this particular relationship holds. And if we look at what this equation says in more detail, we have 2 integrals in this equation. The integral on the left-hand side is the amount of energy in the function little x. The integral on the right-hand side is the amount of energy in the function big X. So what this equation is saying is the amount of energy in the function little x is equal to the amount of energy in the function big X divided by 2 pi. In other words, the energy of little x and the energy of big X are equal up to a scale factor of 2 pi. And the fact that the energy of little x and the energy of big X are very closely related is very helpful to know, since energy is often a quantity of great importance in engineering applications. At this point, I'd like to consider an example to illustrate how we can make use of Parseval's relation. And in particular, I'd like to consider example 6.19. In this example, we're given the function little x, which is defined by this particular equation here, and we're told that little x has the Fourier transform big X, which is given by this highlighted equation here. And based on this information, we're asked to compute the energy of little x. Now, the most straightforward way to approach this problem is to directly compute the energy of little x. In other words, use the definition of energy in order to compute the energy of little x. And if we do this, we're going to simply have this particular integral here, which is the definition of energy for little x. And then we can substitute in for little x the particular function that we're given, which is this particular function here, which gives us this next line. And then we can expand out the sinc function in terms of its definition, which gives us this formula that's written in as an annotation. But this particular integral here is not a very nice one to evaluate, and it's even worse than it looks on the surface. So we'd probably prefer not to compute the energy of little x in this way if we have a better alternative. And fortunately, a better alternative does exist. In particular, we can use Parseval's relation. So rather than computing the energy of little x directly, we compute the energy of big X, which is given by this integral here, and then we use Parseval's relation to find the energy of little x by taking the energy of big X and dividing by 2 pi. So if we substitute in for big X, the particular formula that we're given, which is this highlighted formula above, this gives us this next line here. And then we can use the fact that the rectangular function is equal to 1 between minus 1/2 and plus 1/2 and 0 otherwise to change these limits of integration from minus and plus infinity to minus and plus 1/2. And also we can replace rect omega by 1 in the range that we're integrating over between minus 1/2 and plus 1/2 to get this next line. And then we can cancel one set of 2 pi factors here to get to the next line. And then we can integrate, which gives us the next line. And then simplifying, we end up with a result of 2 pi. So the amount of energy in little x is equal to 2 pi. The next property of the Fourier transform that I need to introduce relates to function symmetry. In other words, the evenness and oddness of functions. So for a function little x with the Fourier transform big X, the following assertions hold. The function little x is even if and only if the function big X is even. and the function little x is odd if and only if the function big X is odd. In other words, a function and its Fourier transform always have the same evenness and oddness properties. Or saying this another way, the forward and inverse Fourier transforms preserve even and odd symmetry. The next property of the Fourier transform that I need to introduce relates to real-valued functions. In particular, we have the following result. A function little x is real-valued if and only if its Fourier transform big X satisfies a relationship of this particular form here. In other words, the function big X is conjugate symmetric. So for a real-valued function, the portion of the graph of x of omega for omega less than 0 is completely redundant, as it's determined by symmetry. For this reason, when we're dealing with real-valued functions, we sometimes ignore the value of the Fourier transform for negative frequencies, since we don't really lose any information in doing so. Using properties of complex numbers, we can show that this conjugate symmetry condition is equivalent to these two conditions here. In particular, if we take the magnitude of both sides of this equation, this yields the first relationship, this one here, which essentially says that the magnitude of the Fourier transform is even. And if we take the argument of both sides of this equation, this gives us the second relationship, this one here, which effectively says that the argument of the Fourier transform is odd. And just as one last comment, I'd like to point out that the function little x being real valued does not necessarily imply that the function big X is real valued. In fact, statistically speaking, this is unlikely to be the case. In other words, if we just randomly choose a real valued function little x and take its Fourier transform, the chance that big X will be real valued is very small. At this point, I'd like to consider 3 additional examples of computing Fourier transforms. And to begin, I'd like to consider example 6.26. In this example, we're given two functions, little x and little y, that are related by this particular equation here, where a is a non-zero real constant, and we're asked to find an expression for the Fourier transform of little y, which is denoted as big Y, in terms of the Fourier transform of little x, which is denoted as big X. Now, as it turns out, the problem that we're being asked to solve in this example is identical to the problem in example 6.15, which we considered earlier when we were introduced to the multiplication property of the Fourier transform. When we considered this problem earlier, however, we were constrained to use a solution technique that employed the multiplication property of the Fourier transform. Now we're going to consider solving this same problem without any such constraint. The reason for doing this is to illustrate 2 extremely important points. First, there's often more than one way to compute a Fourier transform, and second, when more than one approach is possible, different approaches can often involve very substantially different amounts of work. If we now focus on the problem at hand, the most obvious way to solve the problem is to use the multiplication property of the Fourier transform, and this leads to the first solution presented, which is this solution here. Since we've already covered this solution in detail when we considered example 6.15 earlier, I won't go through this particular solution in detail here. It suffices to say, however, that this particular approach to solving the problem, which is based on using the multiplication property of the Fourier transform, is extremely undesirable. Recall from earlier that the multiplication property of the Fourier transform is usually the property of last resort. In other words, because the multiplication property drags convolution into the picture, we normally only choose to use this property when we have no better alternative. In this case, however, we have a much better alternative, and this is why I've chosen to revisit this example now, so we can consider a much better approach to solving this problem. So at this point, I'm going to scroll the example upwards so that we can see the second solution to this problem, which employs an approach that is far superior to that used by the first solution. The second solution is given in this part of the example, and the first observation that we can make is that this solution is very substantially shorter than the first solution. As we'll see in a moment, this second solution is based on using the modulation or frequency domain shifting property of the Fourier transform. By using this property instead of the multiplication property, the need to perform a convolution is completely eliminated and the solution is greatly simplified. With this said, let's examine the solution in more detail. So to begin the solution, we take the Fourier transform of the equation that we're given in the original problem statement, which gives us this particular line here. And then what we need to do next is we need to simplify this Fourier transform, the Fourier transform of x of t times cos of at. And the way we're going to approach this is we're going to rewrite cos of at as a pair of complex sinusoidal terms, which is what appears on the next line. So cos of at has been replaced by this particular pair of complex sinusoidal terms. And then what we can do next is we can use the linearity property. We can interchange the order of the Fourier transform operation and the linear combination that's associated with the operand to the Fourier transform to give us this next line. And this next line has two Fourier transforms on it. The first Fourier transform is this one here, which involves the Fourier transform of a complex sinusoid times the function little x. And the second Fourier transform is this one here, which involves also a complex sinusoid times the function little x. And in order to handle these Fourier transforms, we use the modulation property of the Fourier transform. So if we consider this first Fourier transform, due to the fact that we're multiplying little x by this complex sinusoid e to the jat, the effect that this multiplication is going to have is it's going to shift the Fourier transform by a. So on the next line, rather than having the Fourier transform big X evaluated at omega, it's evaluated at omega minus a. In other words, it's been shifted by a. And for the next Fourier transform on this line, we have a complex sinusoid times our function little x. Due to this particular complex sinusoid, the effect that this is going to have, this multiplication by the complex sinusoid, is going to shift the Fourier transform by minus a. So on the next line, instead of having the Fourier transform big X evaluated at omega, it's evaluated at omega minus a. In other words, at omega plus a. And this gives us our final answer, which is this particular expression here. So the Fourier transform of little y, which is denoted by big Y in this example, is given by this right-hand side. Although we've solved the problem given in this example using two different approaches, it's evident that these two approaches are not equally good. In particular, the second of these approaches, namely the one based on the modulation property of the Fourier transform, is vastly superior. Not only does it lead to a much shorter solution, but the steps required to arrive at the solution are also much simpler and therefore less error-prone. The next example I'd like to consider is exercise 6.5g. In this example, we're asked to find the Fourier transform big Y of the function little y, where little y is given by this particular equation here, and little x is an arbitrary function. Now when we look at this equation, we can see that we're probably going to need to use at least three different properties of the Fourier transform. Because little x is being multiplied by this complex sinusoid, we're probably going to need to use the modulation property of the Fourier transform. Because the function little x also is being multiplied by the independent variable t, we're probably going to need to use the frequency domain differentiation property. And because of this conjugation operation here, we're probably going to need to use the conjugation property. So in total, we have three different properties of the Fourier transform. And to arrive at our final answer, we're somehow going to need to combine all these properties together in some way to produce our answer. Now if we try to combine all these steps together at once, it's very unlikely that we'll produce the correct answers. What we need is a way to more systematically approach this problem by decomposing into smaller, simpler problems, which we can then use to solve the bigger problem. So the approach that I'm going to take is I'm going to start from the equation that we were given, which is this equation here. And I'm first going to reorder the terms slightly in the square brackets. I'm going to group this t here with the x of t, which gives me this next line here. And what I'm going to do next is I'm going to rename t times x of t as v1 of t. Effectively what I'm doing is I'm defining a new function, little v1, which is defined by this particular equation, which I've labeled as equation number 1. And then what I can do is I can substitute for tx of t, v1 of t, because these two quantities are equal. And this takes me to this next line. And what I've managed to achieve here is that this line here that I've highlighted is slightly less complicated than the previous line, because effectively what I've done is I've eliminated this t here by having it absorbed into the definition of v1. So this line here is slightly less complicated than the previous line. Then what I'm going to do is follow a similar sort of idea, and I'm going to group this complex sinusoid with v1 of t, and I'm going to relabel this as v2 of t. Effectively what I'm doing is I'm defining a new function called little v2, which is defined in the manner described by this equation that I've labeled equation number 2. And what this allows me to do is now I can rewrite this quantity in square brackets simply as v2 of t. And when I do this, this gives me the next line, which I've labeled as equation number 3. So the equations 1, 2, and 3 have been rewritten below here, so these are the same equations just written out again, but in a slightly different order. We have equation 3 and then 1 and then 2. Now effectively what we've done with these three equations here is we've taken the original equation that we were given in the problem statement, which is this equation here, and we've decomposed it into three simpler equations, which are equations 3, 1, and 2 that are listed here. And the advantage of writing the original equation in terms of these three simpler equations is, although this particular equation that we started out with is rather difficult to directly take the Fourier transform of, each of these three individual equations, equation 3 and 1 and 2, these equations are much easier to take the Fourier transform of because they're much simpler equations, and in fact each one of these equations only requires the use of a single Fourier transform property in order to take the Fourier transform of the equation. So what we're going to do next is we're going to proceed to take the Fourier transform of each of these three equations. So to begin with, I'll start out with equation number 1, in other words this equation here. So to take the Fourier transform of the left-hand side is fairly straightforward. We have the Fourier transform of little v1, which by definition is big V1, so that gives us this left-hand side here. Then taking the Fourier transform of the right-hand side, on the right-hand side we have a multiplication by the independent variable t. So this would correspond to the frequency domain differentiation property. And what this property says is the effect that multiplying by t has on the Fourier transform is the Fourier transform is first of all differentiated and then multiplied by a factor of j. So you'll see on the right hand side here what we have is we have the first derivative of big X. By the way, the prime symbol here denotes the first derivative, and then we're multiplying by j. Next we consider taking the Fourier transform of equation 2, in other words this equation here. So on the left hand side of the equation we have little v2, so by definition when we take the Fourier transform of little v2 we get big V2, which is this left hand side here. And when we take the Fourier transform of the right side of the equation, we have multiplication by a complex sinusoid, and this corresponds to the modulation property of the Fourier transform. So the modulation property says that multiplying by this complex sinusoid is going to shift the Fourier transform by -5. So down below here we have the Fourier transform big V1, but it's evaluated not at omega, but rather at omega minus -5, which is omega plus 5. And then going on to the third equation, equation number 3, if we take the Fourier transform of this equation, what do we get? Well, if we take the Fourier transform of the left side of the equation, the Fourier transform of little y by definition is just big Y, so that gives us this left-hand side here. And when we take the Fourier transform of the right-hand side, on the right-hand side we have a conjugation operation. So this is going to correspond to the conjugation property of the Fourier transform. And the conjugation property has the following effect on the Fourier transform. First of all, it time reverses the Fourier transform, and secondly, it conjugates the Fourier transform result. So you can see on the right-hand side down below here, due to the time reversal operation, we get this minus sign. Effectively, the omegas have been replaced by minus omegas, and we also get this conjugation operation as well. So now that we've computed the Fourier transforms of equations 1, 2, and 3, we now need to use these results to compute the Fourier transform big Y. Our starting point here is going to be this particular equation, which is just copied to the line below. So this is the same equation here. And recall in this particular problem we're asked to find big Y. So obviously this equation that's highlighted gives us big Y, but the reason that we're not done yet is the original problem statement makes no mention of this quantity big V2. This was a quantity that we introduced into the problem in order to reduce the likelihood of making mistakes in our solution. Therefore we don't want to state our final answer in terms of this quantity big V2. So we somehow want to get rid of it. And what we can do is we can observe that we have an equation above for big V2. So what we can do is we can use this equation and substitute into this line here to get rid of the V2. And once we've done this substitution, what we'll have is this particular line here. So we've eliminated the big V2, but now we have a different problem, which is that we have this big V1 appearing in our answer, which we don't want to be there because big V1 was also something that we introduced into the problem that wasn't in the original problem statement. So we want to get rid of big V1. And in order to do this, we can simply observe that we have an equation above for big V1, which is this equation here. So we can substitute this equation in for V1, and that gives us this next line. And now we've eliminated all these quantities that we introduced into the problem ourselves, the big V1s, big V2s, and so on. So this would be a reasonable answer to give for our final solution, except we can do one further manipulation, which is we can use the fact that the conjugate of the products is the product of the conjugates, in other words this relationship here, and we can replace j by its conjugate, which is minus j, and we can replace this factor here by its conjugate, which is this factor here. And this gives us our final answer. The last example I'd like to consider is exercise 6.2j. In this example, we're asked to find the Fourier transform big X of the function little x, where little x is given by this particular formula here. And if we look more carefully at this particular equation for little x, we can see that there's going to be a number of different properties and or Fourier transform pairs involved in the solution to this problem. Because we have something that looks a little bit like an exponential times a unit step function, probably we're going to need some Fourier transform pair involving a function that looks like that. Also, we have some time shifts happening here, so probably the translation property of the Fourier transform needs to be used. Also, we have an integration happening, so probably the integration property of the Fourier transform needs to be used. And also we have a time scaling operation happening due to this 5 here, so probably we need to use the time scaling property of the Fourier transform as well. So this is 3 properties of the Fourier transform plus one Fourier transform pair that we need to use to solve this problem. Now it's very difficult to try to combine all of these steps together at once and produce a final answer immediately. So what we're going to do instead is we're going to approach this problem in a more systematic manner in order to increase the likelihood that we get the correct answer. So I'm going to start out with the particular equation that we're given here, which is just rewritten on this top line up here in the annotations. And the first thing that I'm going to do is I'm going to group this portion, the underlined portion here, of the integrand into an expression which I'm going to label as v1 of tau minus 1. And effectively I'm going to define the function little v1 as given by this equation number 1. And what this allows me to do is I can replace this portion of the integrand that's underlined by v1 of tau minus 1, just by definition. So if I do this, this gives me this next line. And now what I'm going to do next is I'm going to relabel v1 of tau minus 1 as v2 of tau, where the function little v2 is defined according to equation number 2 here. This then allows me to replace this underlined expression with v2 of tau, which gives me this next line. And at this point what I can do is I can label the entire right-hand side of this equation as v3 of 5t, where the function v3 is given by this particular formula here in equation 3. And then this allows me to replace the entire right-hand side with v3 of 5t, which gives me this last expression here, which I've labeled equation 4. So equation 4 is essentially x of t on the left-hand side is equal to v3 of 5t on the right-hand side. So effectively what I've done is I've taken the original equation that we were given in this problem, this one that I've highlighted, and broken it down into 4 simpler equations, which are these 4 equations that are numbered here, which are just repeated here, except they're written in a slightly different order. We have equation 4, and then 1, and then 2, and then 3. And then the next step in the solution is we're going to take the Fourier transform of each one of these equations. So if we take the Fourier transform of equation 1, this equation here, This is going to involve a Fourier transform pair that we look up in our table, because this particular right-hand side here, this formula is for a function that appears in our Fourier transform table, so we can look up the answer, and that gives us this particular Fourier transform here. Then equation number 2, taking the Fourier transform of this equation, requires the use of the translation or time-shifting property of the Fourier transform. And if we use this particular property, this gives us this Fourier transform here. Then if we go on to equation number 3, this particular equation involves integration. So this is going to use the integration property of the Fourier transform, which gives us this particular Fourier transform here. And then lastly, we have equation number 4, this equation here, which involves time scaling. So to use this, or to perform this Fourier transform computation, we need to use the time scaling property of the Fourier transform, which gives us this particular Fourier transform here. And then in the last step of the solution, what we do is we use this particular equation that I have highlighted as our starting point. So this is just copied down below here. This is this line here. And now we're going to go through a substitution process to eliminate variables that we don't want to express our final answer in terms of. So we don't want to express our final answer in terms of V3 because this was a quantity that we introduced into the problem. So we eliminate V3 by using equation number 7 here, this equation here, which is a formula for V3. So we substitute this equation in for V3 on this right-hand side here, which gives us this next equation, which we can then perform some basic algebraic manipulation to get to the next line. And on this line we have this function v2 that we'd like to get rid of. It appears here and also here on this line. And the way we can get rid of v2 is by using this equation number 6 for v2. So we can substitute this formula for v2 into this line, this line here. And when we do this, this will eliminate v2 and give us this next line instead. And then lastly, we'd like to get rid of this variable v1, which appears here and here. And the way we can get rid of this is by using equation number 5, this equation here, substituting this equation in for v1, which gives us this next line here. And at this point, we can perform some basic algebraic manipulation to manipulate the right-hand side into the form of this last line, which is our final answer.